In Chapter 1 now, Topic 1.7, Combinations of Functions and Composite Functions. These are the functions that we'll be looking at. Now, finding a function's domain. Now, generally, when we are solving for x, these x, as they fit into the real number system, we're wondering what the domain of it would be. So, if a function does not model data or verbal conditions, its domain is the largest set of real numbers for which the value of f of x is a real number. Excluded from the function's domains real numbers that cause division by zero. So remember, anything by zero is undefined. And real numbers that result in a square root of a negative number. Now, if your value is under a radical sign, square root sign, and it's negative, those are not real numbers as well. So we'll point that out as we go along. Now, example 1. So here we have the function of g of x is this, a fraction. And there is a variable in the denominator. Now, what values of this x would make this denominator a 0? Well, the protocol is to equal the denominator to 0, and we can use the square root property, just transpose that negative 49 to the other side, where it becomes a positive 49. Take the square root of it, and plus or minus the square root of 49 gives you the answer x is plus or minus 7. Now, if we were going to plot that on a number line, just to make something a little different, one value would be a negative 7. One value would be a positive 7. And if x were either of these two values, it would make this denominator a 0. So they must be excluded from the domain of real numbers. So graphing it, we would put like a little hollow over the negative 7 and a little hollow over the positive 7, and then darken in the line. These are all the other numbers then. So where I'm darkening in the line, this is what would make up the domain. Now, how would we put this in interval notation? Well, it's coming from negative infinity out here, so we go negative infinity up to negative 7, but negative 7 is not included, so we put a parenthesis there, and then in union, using that union sign, parenthesis on this side starting at negative 7, and now going up to 7, and then parenthesis. Again, 7 is not included in the set. Union, and then on the other side of 7, parenthesis again, 7 is not included, and then going to positive infinity. That would be the domain in roster notation, and that is what we see here. Okay. Now, continuing, we see the algebra of functions, the sum, where we're going to add the functions together, the difference, we will subtract them, the product, we will multiply them, and the quotient, in which we will divide them. And these are all illustrated as to what they would look like. And I've included this in the notes that we will be using to support this. And the key to all this is to be able to understand what's going on. Example 2. So here's our f of x function, which is this. And this is g of x function, which is this. And we want to find the following. What is the addition of these two functions? So we're just going to remove the parentheses here and add them. So there's our x squared right there. Now we have an x right there. Now we have a negative 5 and a negative 1. That's a negative 6. So pretty straightforward. Now, do you think there's any qualifiers of this? Well, there's no values in the denominator that would make the denominator 0. So the domain of f has no restrictions. The domain of g has no restrictions. So therefore, the sum of these two functions for x is all real numbers, which is listed in interval notation as coming from negative infinity to positive infinity. Now, as we move on and look at this, the composition now of functions, and composition means things that are mixed in to be composed, and we note the composition f with g is denoted this way. Now there's a couple of ways to read this. F, so the circle would be the word with G. That's one way. Another way I've seen F, circle G. The composition of F and G, and F composed with G. And it looks officially like this. So this is just the symbolic presentation of the composition of these two functions. Now, the domain of this composition is a set of all numbers such that it would be the domain of the G and the domain of the F. Again, as long as there's no variables in the denominator to be making that denominator as 0, there is no exclusion. All right, let's go on. Now, in example 3, this is what we have just said worked out, and let's see if we can follow it. So given, this is the function of f here, this part right there. And this is the function of g right there. And we want to compose this f composed with g, or f circle g, or f with g. And we said this is the result. So there's our f function with g here. This is the g value. We're now going to put in the 5 from this, because this is the x function right here. Put the 5 in front, and then this 6 is from there. So we're kind of like mixing it together, composing it. Again, this is our x value for g. So where the x is in the f, we substitute this for it, bring the 5 out there, and the 6 is there. So now we distribute this, get 10x squared minus 5x minus 5 plus 6 These are like terms that we can then combine, and then this is the composition of these two functions. Now, I'll read this statement because it applies to this. Excluding values from the domain of this composition. The following values must be excluded from the input x. If x is not in the domain of G, it must not be in the domain of the composition of f with G. Any x for which the G of x is not in the domain of f must not be in the domain of its composition. Now that's the statement and maybe somewhat unclear. We'll see if they give us an example. All right, example 4 now, where we're looking at forming a composition function and finding its domain. Well, as you see this, I don't know if you can see what the problem is here. What value would make this denominator, the x in the denominator, a 0? Well, here it would be a -2. So x could not be a -2. And then here, x could not be a 0. Any other number is fine. So you do have some excluded values. Now here's our given function f, where we're going to compose this into f. So we're going to take this and put it where the x is here. And that's what you see here. Now, to get rid of the fraction, and let me write this on the whiteboard for you. And you see how we get this. We're just copying this. Now going to the whiteboard, how do I get rid of that x in the denominator of a fraction in the denominator? Well, the protocol is, what's my lowest common denominator here? Well, here it's going to be an x. So I can multiply any fraction by 1. But the form of 1 that I'm going to use to clear that is x over x. Now, would you all agree that x over x is 1 as long as x is not 0? All right, so we multiply the numerator and we just get 4x. That's easy. Remember, this is in parentheses. So now, x times this fraction, the x's cancel out, and this is just a 1. So multiplying this 1 over x times x, the x's cancel out and we just get 1. And this becomes 2x. So there's our simplified fraction now. And let's go back to the other screen. And that's what you see here. So just to be sure you know where it came from, that little square tends to be a tad confusing. Now we're calling this example 5, but it actually relates to the previous example. We now want to find the domain of this composition. Now remember, in the denominator, you can't have a 0 as a denominator because that would be undefined. So over here, what value of this x would make this denominator a 0? So we just solve it. We go 1 plus 2x equals 0. We transpose the 1. That becomes a -1. And we still have 2x. We're going to divide both sides by 2. we get x equals a negative 1/2. So if x here is a negative 1/2, that would make this denominator a 0. So we have to exclude this value. Now we said we also excluded the value up here where x could not be 0. We said that in a previous slide as well. So let's put this on a number line, and hopefully that helps with this a little bit. So there's my number line. Now we have to exclude a negative 1/2. So there'd be a circle there. And we said we have to exclude 0 itself. And that would be a hollow there. So as you see, we're coming from negative infinity here up to a negative 1/2. That has to be excluded, so we use a parenthesis. Union on the other side of this, negative 1/2, because negative 1/2 is excluded, and this goes up to 0, and then union again, and starting on the other side of 0 to positive infinity. And this is what they're showing here too. I just thought it was interesting to see it visualized in this way. Now, so far we were composing, but how about if we were to decompose, what might it look like? Okay, so we're going to look at that. We saw how taking two functions, putting them together, but what might it look like if we decompose something? And let's take a look at this one. This is example 6. Now we want to separate this into two parts. And we'll just use what they have here because this is nice. And this is a very easy example. So if we had f of x was equal to the square root of x, and g of x was equal to x squared plus 5, if we compose these, f composed with g, we would take this and put this where that x is, right there. And we would end up like this, which is, we're using the letter H now to express the composition of these two, but then spreading them apart to show decomposition. So if you can go one way, theoretically you can go back. Now it might not always be the same, but it would be a decomposition. Okay, this was somewhat of a short lesson. And again, vocabulary and being exposed to formula and vocabulary.